Okay, can we begin now?
University of Science and Technology, and his research interests include classical and quantum code theory, information theory, and code-based masking. Let's all welcome our speaker.
Good morning, everyone. Today I will introduce the talk about partially concatenated CSS codes achieving the quantum GV bound asymptotically. This is a joint work with Jun Li, Ya Wang, Yonghui Li, Minxiu Xie, and Jiangfen Zhu. Here is the outline, and here is the abstract. First, I will introduce some background about stabilized codes and some classical linear codes. A stabilized code is a QK dimensional subspace of the Hilbert space, and here is the definition of a stabilized code. And the S, the group S is called the stabilized group. And Q and the quantum code Q is called non-degenerate if S does not contain a non-trivial element whose weight is less than D. Otherwise, it is degenerate. And here is the famous CSS construction. That is, if we have two classical linear codes that satisfy the dual containing condition, then there exists a stabilized code with the parameters. Also, there exists an enlargement construction of a CSS code, which is given by Steane. And the enlargement construction of CSS code needs a nested pairs of a classical linear code like this. Then we can see that the minimum distance of the enlargement construction of CSS code is maybe improved by this factor. Also, we have an asymmetric construction of a CSS code because in many quantum channels, the error probability of the errors is much larger than that of X errors. So this phenomenon exists very general in quantum channels. So we need two classical linear codes. For example, a CX and a CZ. And CX is used to correct X errors, and CZ is used to correct the errors. And the distance of CX, CZ, and CX is given by like these two equations. Here we need to introduce the famous Beck-and-Shor codes. Beck-and-Shor codes have some relationship with our constructions, so we need to introduce some very basic knowledge about Beck-and-Shor codes. Let C1 and C2 be any two classical linear codes. Yes, any two classical linear codes, and they do not need to satisfy the dual containing constraint. And the Beck-and-Shor code constructs two parity check matrix, HX and HZ, like this. So it is easy to see that HX and HZ can satisfy the dual containing constraint for classical linear codes. Yes, because we can see that G1 and H1. G1 is the generator matrix of C1, and H1 is the parity check matrix of C1. So because G1 the product of G1 with the transpose of H1 is equal to zero matrix. So Hx and actually the product of Hx and the transpose of Hz also satisfy the dual containing constraints. Then we can obtain stabilized code with the parameters like this. For example, the Shor-Steane 913 code, yes, is a back-and-short code, and it was shown that back-and-short codes have high fault tolerant threshold. Also, the back-and-short codes are degenerate codes. However, back-and-short codes are asymptotically bound because the minimum distance of back-and-short codes is usually about square root of the code length. Also, we give an introduction about hypergraph product LDPC codes. Such codes were given by Tillich and Lemot. Yes, given by Tillich and Lemot. And the hypergraph product codes have some similar structure with back-and-short codes. Yes, we can see below. Also, let C1 and C2 be any two classical linear codes. Yes, they do not need to satisfy the dual containing constraint. And Tillich and Lemot construct two parity check matrices, Hx and Hz. And it is not difficult to verify that Hx, the product of Hx and that of the transpose of Hz is equal to zero matrix. So they can obtain a stabilized code with the parameters like this. So this construction can obtain a very good quantum LDPC codes, yeah, with good parameters, and many related works have been done to improve for example, the minimum distance of the hyperproduct LDPC codes, and recently the famous quantum LDPC conjecture was solved by two researchers from Russia. I think the pioneer work about the quantum LDPC conjecture was given by Tillich and Lemot. Here I introduce the structure of partially concatenated CSS codes. Also, we let C1 and C2 be two classical linear codes, and we call them the inner and the outer codes respectively. Here we have to notice that C1 and C2 can be seen to any two classical linear codes that do not need to satisfy the dual containing constraints. However, the parameters of C2 have some constraints because the length of C2 is K1, which is equal to the dimension of C1. And we construct two very simple parity check matrices, Hx and Hz, like this. Hx is H1 multiplies with the H2 multiplied with G1, and HZ is H1. Also, G1 is the generator matrix of C1, and H1 is the parity check matrix of C1. Also, the H2 is the parity check matrix of C2. Yes, the structure is very simple, and in some content, it seems that the structure is very trivial, because it is very easy to verify that Hx multiplied with H, the transpose of Hz, is a derive matrix. Yes, the derive matrix. So we can we can construct a quantum code by using the CSS construction very easily, and we can obtain the so-called partially concatenated CSS code, because we only use the concatenation in the Hx part, and so we call it partially concatenated. And the parameters about the code length and dimension of our queue is very can be obtained directly. Yeah, it seems that it seems very simple. However, we can see that the minimum distance of queue was not determined, and we need to compute the minimum distance of Q. So here we have a conclusion about the asymptotically good partially concatenated CSS code. That is, there exist partially concatenated CSS codes with parameters like this, which can achieve the quantum GV bond asymptotically. Here we give a introduction about the proof. Let C1 be any classical linear code, and let C2 be an alternate code. I will explain why we use alternate code why we use alternate code. And C1 can be any classical linear code, yes. Then by using the CSS construction, we can derive a partially concatenated, yes, a PC CSS code with the parameters like given by this equation, and dq is given by this equation. We can see that omega 1, yes, omega 1 is larger than or equal to d1, and d1 is the minimum distance of c1. So the lower bound of omega 1 it can be determined. Yes, it is d1, and because c1 can be any classical linear code, so we obviously we let C1 be some good codes. For example, linear codes that can achieve the classical GV bond. The problem exists in omega 2. Yeah, omega 2. Yeah, yes, we let C1 be an asymptotically good linear code. So the problem exists in omega 2, and omega 2 need to be determined next, and we denote by SV as this equation. It can we can see that SV can be seen as the syndrome of the dual code of C1. Because the structure of the PC, the so-called PC CSS code, is given by Hx and Hz, and the V is a an arbitrary vector. So SV is can be seen as the syndrome of the dual code of C1. If SV is equal to 0, then V must belong to the dual code of C1, and V is degenerate when we compute omega 2. Yes, because V is belong to the dual code of C1. Yes, and actually is equal to H1. So although SV, if SV is equal to 0, some bad things may happen, but it is degenerate, so it do not affect the computation of omega 2. Therefore, we only need to consider the case which makes SV not to equal to 0. Sorry, wait a few minutes. I have a few seconds. I have some personal affairs to tackle with. Okay, I come back. And the number of alternate codes. And the number of alternate codes, yes. Sorry. The self-dual codes is about is in the discussion part, and I write it here. We can only see about the alternate codes. The number of alternate codes that contain any non-zero vector does not relate to the Hamming weight of SV. This is the key points of our proof. And another. Okay, and another code we will find that satisfy the constraint is self-dual codes. That is self-dual codes also that contain some any non-zero vector also does not relate to the Hamming weight of SV either. That is why we choose alternate codes and the outer code. Yes, that is why we choose alternate codes and the outer codes. Once we find that the number of alternate codes that contain any non-zero vector does not relate to the Hamming weight of SV, we can use the very classical counting arguments for classical linear codes to show that PC CSS code can achieve the quantum GV bound. Yes, that is the following is some very classical methods that to prove the classical linear codes achieving the classical GV bound, and we use to prove our result. Yes, this is the outline about the proof. Then we have a corollary. That is, there exists asymptotically good asymmetric PC CSS codes such that they satisfy the asymptotic bound like this. Because in many in some construction of quantum codes that can achieve the quantum GV bound. That many of those results cannot obtain asymmetric quantum codes that can achieve the quantum GV bound for asymmetric codes. although it seems that it is a very direct generalization, but very few results exist. So we give a corollary for the asymmetric quantum codes. Here we show that we use the corollary to show that PC CSS codes can approach the hashing bound for polychannel. Here is the polychannel, the classical polychannel, and we denote the total error probability by P, and denote by theta the asymmetry for the probabilities of Z errors and X errors. And usually we let Px be equal to Py. Then we have Px and Py given by these two equations. Since C1 can be chosen arbitrarily, we let it be an LDPC code. And we know, we know that LDPC codes can approach the channel capacity of the binary symmetric channel under the BP decoding. And also, we let C2 be an alternate code, and it can be decoded up to the GV bound under the bounded minimum distance decoder. Then the rate of the partially concatenated CSS codes under the asymmetric polychannel can approach the hashing bound like this one. Not the hashing bound, sorry, can approach the bound in this equation. And next we compare the bound in for example in equation 12 with the hashing bound of polychannel. Here is the comparison. Sorry, there is a mistake about the abbreviation. We can see that, for example, the solid line is our code. The solid line is our code, and the dashed lines is the dashed lines are the hashing bound, and they have different channel asymmetries. Matrices. For example, theta equal to 1, 100, and 1000. If zeta is equal to 1, then the asymmetric channel is a standard symmetry channel. We can see that if zeta is equal to 1, the bound of our code, there is a large gap between our bound and the hashing bound. However, as the asymmetries goes too large, yes, as the asymmetry goes too large, and the gap between our code and the hashing bound is becoming smaller and smaller. And if the channel asymmetry goes to 1000, and 1000 is a very common asymmetry in quantum channels, then we can see that our code can approach the hashing bound of asymmetric quantum channels. Yes. Next, we introduce a family of fast encodable and decodable partially concatenated CSS codes. Because we find that our codes, if we choose some particular classical linear code to construct the partially concatenated CSS codes, we can obtain a family of fast encodable and decodable quantum codes. Here we only give the conclusion, and the the particular classical linear code we choose is the sorry, I forgot. It's the sorry, I forgot let me have a look at the papers. The expander code, yes. The particular classical linear codes we used to obtain the faster encodable and decodable codes is expander codes. Also, expander codes were used to construct quantum and LDPC codes. We here the theorem is very general. Here we pay attention to corollaries, which are given by this in this page. There exists a family of quantum codes with the following parameters. Yes, the code length is n, and the lower bound of the code is the square root of n, and the distance is also the square root of n. And then Q1 can correct all errors of weight smaller than half the minimum distance bound in linear time. Yes, in linear time. And Q1 can also be decoded in parallel in square root of the n's by using the square root of n classical processors. We also show that Q1 can be encoded efficiently by a circuit of size O linear size and depth. Moreover, Q1 can correct a random V error with very high probability, provided PZ is less than 25%. Here we have some instructions about the corollary. The total decoding time completed is Q1 is indeed O(n) plus O square root of n. So the decoding probability is indeed O(n). However, we want to say that the decoding complexity of the x part is the square root of n due to error degeneracy, and the decoding complexity of the v part is O1. Here the error degeneracy does not play. So we want to say that we want to discuss that where there exist quantum codes with such parameters, which can be decoded in square root of n time, and because such decoding time may cannot be found in classical linear codes, but in quantum we can if we explore the error degeneracy, it is possible to lower down the decoding time of quantum codes. Here we only get x part due to error degeneracy, but for the v part we do not get the improvement. Here is another corollary, and there exists a family of quantum codes with the following parameters. We can see that the dimension is almost linear, and also the minimum distance, or for example, the v distance is also almost linear. Then Q2 can correct an almost linear number of z errors, and can also correct a linear number of x errors with a high probability in linear time. Further, Q2 can be decoded in parallel in log time and by using linear classical processors. So the two colories may be useful in fault-tolerant computations because we can because Q2 can correct, for example, Q2 can correct an almost linear number of the errors, and can also correct a linear number of x errors with high probability. And here is the encoding circuit of the partially concatenated CSS code. Moreover, we gave an enlargement construction of a partially concatenated CSS code, which can achieve the quantum GV bound for Steen's enlargement construction of CSS codes. We can see that the GV bound for enlargement of partially concatenated CSS code gets improved by this factor. Here is some instructions, and the partially concatenated CSS codes can be used to prove the security of the famous BB-4 quantum key distribution protocol. We can obtain the total qubit error rate for the security of BB-4 over Pauli channels is less than this one, although it is lower than the bound of given by Shor and Preskill. And our codes are not randomly generated, and the LDBC component codes can be efficiently decoded. And another discussion is about whether our codes in corollary 1 and corollary 2 can be used in fault-tolerant quantum computation, and how to compute the fault-tolerant threshold. Okay, that's all. Thank you. Any questions?
Thank you very much for your presentation.
Thank you, Lando.
Does the audience has any questions for the speaker? I think we do not have any more. So let me thank you again for agreeing to give us your talk and for this presentation.
Okay.
Yeah. And okay.